So right now we're going to talk briefly about percent error and proportions. So percent error is basically a way of determining how accurate your measurements are. So percent error is calculated of value, the experimental value, minus the accepted value divided by the accepted value. Okay, and then times 100% because it is a percent error. Okay. So basically, experimental value is whatever you measure, and then the value accepted is what the value is supposed to be. Okay? So there is some error or uncertainty that is always expected in any measurement. So this goes into the skill of the measurer, how many times they've taken this kind of measurement, the conditions of the measurement, and then also the measuring instruments. Okay, because each instrument, if it's a highly technical instrument, maybe it needs to get calibrated, or, different kinds of things can throw them off and all that kind of stuff. So there is some error or uncertainty that's always expected in any measurement. So using this, okay, a student measures the mass and volume of a substance and calculates its density as 1.4 grams per milliliter. The correct or accepted value of the density is 1.3 grams per milliliter. So what is the percent error of the student's measurement? Okay, so oftentimes we will write percent error as just a PE. Okay, so PE, that's an E. Okay, so the value experimental, again, this is the one that the student measures, calculates everything. So that's the 1.4. Okay, and then you want to subtract out the actual value. So if you have a positive number at the end of this calculation, that means that you overshot the actual value. If you have a negative, it means that you undershot it. Okay, so it can be a positive or negative percent. So then we've got 1.30, okay, is the actual, and then we're going to divide it by the actual. So this gets you a percentage of the actual value that you're off. Okay, so if this actual value is very large, okay, generally you will end up with a smaller percent error. Okay, if it's a very small value, then it's going to be a very difficult task to get it right on. Okay, so you'll end up with a larger percent error, right? And then you also, of course, want to multiply it by 100%. Okay, so if we do this calculation, we've got the 1.4 minus 1.3, okay, and then divide that by 1.3 and multiply by 100. So you end up with your percent error is 7.69 and then percent, because you did multiply it by a percentage. Okay, so you are almost 8% off of the actual value. Okay, usually it's considered a fairly accurate reading or fairly accurate measurement if it's under 5% off. Okay, sometimes that can go up to 10, especially depending on how sensitive the measurements are, how small the actual value is, so on and so forth. Okay, but yeah, so in this case, it's a fairly decent measurement and calculation, but it's not the greatest. So you always want to examine your answer to determine whether or not your answer is reasonable. Now, this goes with really any calculation. Okay, so if you are asked to calculate the number of seconds in a year, if you end up with just a really small number of seconds, got to think about that. If 60 seconds are in a minute and you have, say, 45 seconds, that is not the number of seconds in a year. So you got something in your calculation off, so you need to go back and look at it again. Okay? So check to see that your units are correct before you do any calculations. That is a major thing that I've seen throughout science classes, is that if there is, say, one unit that's in kilograms and then the rest of them are in grams, most students do not catch that kilogram. Okay, and then that throws off everything. Okay, because you're basically cutting out a couple thousand grams, okay, depending on the size of the kilograms. Also, know what units the answer needs to be in. So if you've got kilograms, but it's asking for the answer in grams, you do have to convert everything to grams, no matter if everything's in kilograms or not. Okay? Everything has to be in the units that the answer needs them in. Then make an estimate of the expected answer. So this is what I was talking about with the seconds and the years. You don't have to be perfect on this, but this helps avoid a lot of calculator errors. Okay, so if you're trying to calculate the number of seconds in a year and you get 45 seconds, okay, that is obvious that it's way off. Okay, because 45 seconds passes in less than a minute. So you got some really funky years if that's how many seconds there are in a year. And then also check the order of magnitude in your answer. Okay, now this is more once you get into kind of like when we start talking about moles and the number of atoms in something and all of that. This goes into the exponents. If you start off with something that's 10 to the 23rd, but your answer is 10 to the negative third, okay, there better be a pretty big something that you divided it by, okay? So we'll get more into that step later, and then also be sure that the answer given for any problem is expressed using the correct number of significant figures. Now, there are some teachers that are huge sticklers on this. I am not one of them. Okay, I mainly teach significant figures because I've seen so many students get to the next level in science classes where it is required of them and they have no idea what to do with significant figures. And it's a lot harder to learn something like that in a class where they basically expect you to already know it. And so they rush through that. And they might spend maybe 5-10 minutes on significant figures, and then that's it. And you are expected to know it because it's supposed to be a review. Okay, so that's why I always talk about significant figures. All right, so sample problem. This is getting into kind of manipulating your density formula. So let's go ahead and work with that. We've got density equals mass divided by volume. Okay, now once you put the numbers in, a lot of students can get kind of confused. Okay, so I like to teach how to kind of manipulate this formula before we even get to any of the numbers. Okay, so if you're trying to calculate, say, the volume, okay, you can say that this density is over 1. Okay, so putting something over 1 is not going to change that value because if you divide by 1, you end up with the same value. Okay, but that allows us to see cross multiplication a little bit easier. Okay, so if we're trying to solve for, say, the volume of something, okay, we want to cross multiply here. So we end up with volume over 1 equals mass over density, or volume equals mass divided by density. Okay, easy way there. Now if we're trying to solve for the mass, okay, so let's go back to density equals mass divided by volume. You need to get rid of this volume on the mass side of the equation. So you multiply both sides of your equation by the volume. Okay? And so that gives you volume times the density equals your mass. So in that way, you've just manipulated your formula, so now you're solving for each of the 3 variables. So we started out solving just for density. Okay, you solve for density by taking the mass, dividing it by the volume. Then, if you want to solve for the volume, you take your mass and divide it by the density. Okay, And then if you want to solve for mass, all you do is you multiply your volume and your density together. Okay? So that's how you can manipulate these around, these formulas. And you will see a lot of formulas that just have 3 variables in them. So you need to know how you can manipulate things just to kind of move them around. Okay? Now if you don't want to manipulate the the variables like we just did here before plugging numbers in, that's up to you. I just find that it can be a little bit easier sometimes to work with the letters and then add the numbers in. Okay, so here in this problem, we're calculating the volume of a sample of aluminum. Okay, so volume here, we've got this formula right here. That is your volume, or to solve for volume. Okay, now there's another trick in this problem that you have to be careful of. So look at your units. You have kilograms here, you have grams here. So you can't just plug the mass in as it is and divide by the density. Okay, you actually have to pay attention to these units. Now, generally, I try not to mess with units in a derived unit. Okay, so I leave the grams per centimeter cubed alone, right? So we've got just kilograms on this side over here with the mass. Okay, so that's easy to change into grams. Okay, so if we've got 3.057 kilograms, okay, I know from my King Henry died by drinking chocolate milk that I need to move my decimal place 3 places to the right. Okay, so then I have 3,057 grams. So now I can go ahead and plug this into my formula. So I've got volume equals my 3,057 grams over my 2.70 grams per centimeter cubed. Okay, now when you do this, this will actually cancel your grams out and leave you with just centimeters cubed. And because our problem does not ask you for the volume in a specific unit, you don't have to worry about changing that at all. Okay, so all you have to do here is just go ahead and calculate it. So it's 3,057 divided by 2.7. And we end up with 1,132.2 repeating centimeters cubed. Okay, now if you wanted to, you could transform that into meters cubed by just moving your decimal place 3 places, but honestly, leaving it that way is perfectly fine. Okay, so 1,132.2 centimeters cubed. Now, again, if you don't want to manipulate your formula, you are perfectly welcome to just go ahead and plug your numbers in. Okay, now again, you do have to be sure that you've got your units correct and all of that stuff. Okay, but if you wanted to do it that way, you could just do your density. That's not supposed to be B. Okay, let's just erase that. There we go. Okay. So you can do density equals mass divided by volume, solving for volume so you don't know it. You've got your 2.70 grams per centimeter cubed. Okay, and then that's equal to your 3,057 grams over volume. Okay, and then you just solve for your volume. You will end up with the same answer. Okay, so I'm not saying that you can't just go ahead and plug numbers in, but sometimes it's easier for students to visualize the letters moving around than it is for them to visualize the numbers moving around. Okay, so that is it for this video, and we'll pick up in the next one.